One thing I forgot. Code everywhere.
So we are so glad to see you on campus. There are a few things that we need to let you know before we start the lecture. First, please make sure that you have your mask on all the time when you are in the classroom. Also, please make sure that when you are having a seat, try to keep a social distance with others if possible. If you feel sick, no matter it's physically or mentally, please stay at home. We do provide various online resources to keep you learning. Now, please sit back, relax, and enjoy the lecture.
All right, so today we are going to continue our discussion of file systems. And in the last lecture, we talked about the basic idea of file system is provide a unified abstraction for everything that is not your processor. Well, that's not true because in Unix, everything is file, right? So file system as an abstraction of everything, right? So, but in fact, if you think about file system, it's actually an abstraction of everything other than processor and memory. But Unix actually extend that abstraction. So, but at least one thing you know, right? No matter what file system can stand for your for your operating system, is a very important part of the of modern operating system. So today we are going to see the design of this file system. But before we start, let's have a brief recap on why we need a file system. So the main reason is because if you look at how you interact with the device, you have to, if you want to directly interact with them, you have to use their address space. For example, the label of the block. Or if it's not a storage device, like an accelerator, which you have to deal with in your project, right? It may be something else, right? So, and it turns out that if you don't have an abstraction that makes it easy for the applications to interact, to talk with, then every application have to figure out where my data is every time when you need it, which is not realistic and not portable for your applications. So it turns out that we need this abstraction called file system. And with the file system, what you could do is that you just need to tell the system, this is the file that I want to open, I want to manipulate. And then the library together with the file system will figure out what are the addresses, what are the set of addresses that you are accessing, and translate your read command to a set of hardware commands that help you to locate the data, help you to fetch the data, help you to place the data in a buffer that you can later on manipulate. So that's the idea of file system abstraction. And then in Unix, right, they extend the file system abstraction to everything, as I just mentioned. It's not just a logic unit of storage. It could also also be a device or a directory or anything, right, that could be abstract as a file. So for example, in Unix there is, or Linux, there is a directory called /proc. Each process is essentially mapped as a file in the /proc. And what is a file system? Is a system that has a collection of files and that manages files. And so the file system, there are several elements in there. So for example, how these files are structured. So you know, for Unix, we have the hierarchical structure, which tells you that the files can be under directory, a directory can be under another directory. That's hierarchical. And you can also have a namespace of the file. And also, so for example, like the Unix, you can have arbitrarily long string as the file name, right? And it provides persistence because now you know once I place the file in a file system, it should be there, and it shouldn't, unless I issue the command called remove, it should always be there, right? It controls the access. For example, my file shouldn't be seen by another group of people which I'm not authorizing, and other protection security mechanisms. And because the file itself provides this mechanisms for protection for security, so that's why Unix love it, right? Because if you implement your process as files, this access control protection security mechanism can inherently apply to those process management as well. And the most important thing, right? Even for systems that are not Unix, the file system provides an abstraction for secondary storage. So everything that you store on the second storage is essentially a file. So now you should be aware that operating system, we have these abstractions, process, thread, virtual memory, which you learned before the midterm. And now you have a new abstraction called files. And today we are going to talk about the old Unix file system, the BSD fast file system, and the log structure file systems. So we say that, right, in the past, that in the last lecture, that we label the blocks, or say the sectors on the disk with numbers, and starting from 0 to the end of how the number of blocks you have. And so a very naive, very direct way that you would like to use this file system. So it's directly used from the very beginning of the space, right? So that's how Unix old file system try to use the files, try to use the secondary storage. And regardless of that, right, there are still tons of questions that we want to answer in designing a file system. So for example, once I place some data in there, right, and what I just mentioned is that the good thing about file system is that you don't have to remember the address of the block. It's the file system's responsibility. So how the file system knows how to translate those file names to the location, right? And how do we allocate the number space that you just see in the storage device? And how? And well, when you want to allocate it, you know, because of the characteristics of your storage device, as I mentioned, right? The disk would rotate, right? If there is a way we can make this file system fast enough to accommodate the fact that you have to rotate the disk, and how to ensure that the file, once you put it there, it will be persistent. It won't be gone, right? So those are the important issues about designing the file system. So for the old Unix system, the most simple naive way is that, okay, starting from the beginning of the disk, we place some important data that is about the file system itself. So this part of data is called file system metadata. File system metadata. So it's the metadata of file system. So metadata means those data that are not your content. So the the file system metadata actually stands for the information about the file system itself. So for example, how big is the file system? How many free blocks that I have? What are the list of free blocks? Right. So those are the information that the file system metadata would store. And followed by the file system metadata is file metadata. So a little bit confused, right? Metadata, again, the definition of metadata never changes. It means the data that are not your content. And file system metadata is the metadata related to the file system itself. And to distinguish from the file metadata, we typically call the file system metadata as super blocks. And for file metadata, that's the metadata of the files you store. Can you hear the difference? Super blocks are the metadata associated with the whole file system regarding how many free blocks we have, regarding how many blocks we have, regarding the locations of the file system. And the file metadata is just about each single file, the metadata of each single file. And another name for the file metadata is called inode. Right, so you have super block as the file system metadata, you have inodes as the file metadata. So the inodes typically contain information about what we just said, the permission of a file, the security perspective of the file, and the locations, which means if I want to locate the real content of this file, where are those blocks? So followed by this, the rest part of the disk will be used for real user data. That's the most simple naive layout of a file system. I start with the file system metadata, then a set of metadata for files, and finally the file content itself. Right? And as I said, right, the super block, the metadata of the file system contains this information, and the inode is the metadata of each file contains the file type. And remember, right, here when we say file type is talking about if this is a directory, is this a regular file, or if this is a device file, right? Not to the degree of file types that you are aware of. It's not about if this is video content, if this is music content. No, it's just about if this is a directory, if this is a regular file, or if this is a device. And the size of a file, the permission, the attributes. Right? So those are the stuff that an inode will store. And this is a typical layout of a Unix inode, which it first talked about the file types, the size of the file, the permission, the attribute, and a few other pointers here is telling you, if I want to find the user data, the data content of this file, where can I find it? So there are three types of, there are actually 4 different types of blocks. So the first one, the first type, the first group of them is the direct blocks. So this is just a list of blocks that here are directly the addresses of the blocks that this file holds. However, if my file is larger, then there is going to be a single indirect pointer to another set of single indirect tree, which pointing to another list of this, which give you more space to tell you where the data are. And then double indirect, which give you this type of list of data blocks, like the second level tree, right? And finally, if you are running out the double indirect, you can build triple indirect. And as you can imagine, the triple indirect would be something like this, and each of this would be linked to a set of data blocks, right? So this is, so with this total thing, right? This direct, single, indirect, double, triple indirect, the conventional Unix file system can have at most 8 gigabytes of data per file, which to your perspective is big enough, but you can definitely find bigger ones, right? So for example, if I have a Blu-ray, it's not going to be enough, right? So, but remember, this is a very old design starting from 1970, right? So definitely we are evolving, right? So now, but remember that was the old Unix file system. So right now, think about that, right? Think about from your understanding, right? From your understanding, from your reading of the Unix old file system. If I want to access this file, how many, and if there's no cache, how many disk accesses we need? All right, let's wrap up in 10 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so look at what you guys think. Okay, so a lot of you think is C, but I think this question would be worth discussing. So why don't you go ahead and discuss with your friend for another minute or two. What do you think? All right, let's wrap up in 10 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after discussion, okay, more of you think it's C. So I want to hear someone online. What happens during your discussion? Will that encourage more people to come in person? Let me see. So that's starting from group one. Anyone want to raise your hand in group one? So here I have, let me see, I have James, I have Jeffrey, I have me here, I have Moha, I have Vinay, I have Yichong. Anyone want to share your thoughts? Group one. Who's in group one? Anyone online in group one? Akashi, Aditi, James, Jeffrey, Mohar. Anyone? Hello? Somebody there? Okay. You got it.
I tried
Yes,
to
I
speak
can
up,
hear
but
you.
I guess we had some glitch. We couldn't have any discussion. I marked an option A, but I couldn't have any discussion with any
So
person.
you mark the option of what?
Hello?
What did you pick?
I marked A.
Hello?
I marked A.
E.
A.
Okay. And you say the reason why you don't have a discussion is because?
I don't know. Maybe we have some glitch.
Okay, so then, okay, that will be interesting. Okay, so so here's the thing. I will randomly put my TA into any of the group online. If he didn't hear any voice within 10 seconds after he joined, the TA will let me know, and the attendance of your group, the whole group, will become 0. Okay, because the purpose of this is that I want you to discuss, right? And I already do not ask you guys to, get the absolutely correct answer, right? So it's important that you guys discuss, right? So if the TA didn't hear you discuss in 10 seconds, you don't have to discuss for the rest of the class because the attendance will become 0. Okay, hopefully then you guys will shout out, right? I don't believe, so you guys have at least like 11 people in a group, and I don't believe all 11 people's microphones are done. Okay, all right, so Maha, can you share why do you think is at least 10?
Yeah, sir. Actually, I said A 4
Mhm.
given the size of a path.
Oh, you say 4. Okay, why 4?
The size of a path. That's it. I mean, I don't have any strong reasoning behind
So
that.
you said that the home way, the CS202 will fall down C.
Yes.
Shouldn't it be 5? Who said 5?
Yeah, 5.
Why?
Root.
Okay.
Home root.
Root is a directory, right? Okay.
Home root, CS202 and 2. So that's 5.
But there is no option 5.
Yeah, there is no option 5.
So then you should pick B.
How do you repeat?
But a lot of you chose C. Why? There is a metadata, right? So some of you figured it out, right? So how did you get the address of home?
From root.
From root, but where in root?
So that's the
Right, that's a metadata, right? So here's the thing. What's inside? Okay, so the root itself, right? That's a directory. A directory is a
file.
right? Okay, so tell you a trick, right? So because in Unix everything is a file, right? If I have a blank that I want you to fill, then I ask, a process is a file, right? A device is a
File.
right? Everything is a
File.
right. So if you answer file, it will never be wrong, right? So that's the trick, right? So you are right. A directory is a file, right? So the thing is that the directory itself is a file. But what's the content of the directory? It's actually a list of files. Yeah, a list of files, but are they the list of the file content? The pointers to what? To the inode of another file, right? Right, so from the root, I get a list of inode, right? One access, right? And then from this one access, then I go to I go to an inode of home, right? Inode of home, right? Inode, that's one, right? Then from the inode, I got a list of addresses where the content of home is. And what's inside the content of home? Another list of inode, right? But to get the content of home, that's another access. So two here, right? So one more. So the same thing you can imagine, right? So when I access the home, I will also get the inode of home way, then the content of home way. The inode of CS202, the content of CS202, right? The content of 4.c. The inode of 4.c and the content of 4.c, right? So now a total of 8 plus this, right? So it should be 9, but why am I saying at least 10? The metadata of the process and yourself to figure out where the root is. Right. A total of 10. Did you get it? Right? So here's the thing, right? It's a lot, right? You have to open the root file, which is from the super block, locate the entry of home, open that file, locate the entry of home, open that file until you reach the end, right? So what will happen is that super block access, then figure out the root, and it will tell you the inode of the home, right? And then go to the home's inode, and it will tell you where the content of the home is, and figure out there is home way here. So you go to the inode of home way, and then figure out where the content of home way is, and go there, and it will tell you where the next file is, right? And then here we go, right? So a total of 10, right? So that's a lot, right? And so and if your file is spread across multiple blocks, then you definitely have to have more than 10. So that's why I'm saying at least 10, right? Because sometimes if your file content is more than 512 bytes or the block size of the file system, then you need to access more of it if there's no cache, right? So that's a lot, right? So you think, well, access a file is simple and easy question?
Yeah, so I was wondering, so if there, as you said, more than 500 bytes of data, so there will be another node for like rest of the file. But
so the thing is that, right, the inode, for the inode, there's a list of, so for example, right, like there is a list of data blocks belonging to this file. So once you have the inode, open, you have the list of the file blocks, right? And then if you cross the file blocks, you have to initiate another access to the next file block.
But I mean, is it possible for if we have like so many files in node that it can fit inside the node?
So many files in a node.
Yeah, so many addresses.
That's possible, right? So if you have, although, right, remember for the content, right, the content itself can be 8 gigabytes, right? So, and each of this, like this list is just a pointer, right? So you can store 8 gigabytes divided by, for example, 8. This amount of files in a list, which is a large number, right? But you are right. In the worst case scenario, it may run out of that.
So what happens?
Well, then it will figure out that well, it will just give you an error. Yeah. Yeah, but it will happen. You're right. All right. So that's the basic idea of Unix file system. Old Unix file system, as you can see, there are tons of problems, right? So first of all, if I want to get a file, a lot of accesses, right? And also, you mentioned a good point, right? There is limited amount of data we can accommodate, right? 8 GB in total, which is not enough in many cases now. So, so they have this fast file system proposed for BSD systems. So let's see, why do we care about the fast file system? Again, right, in the very beginning, Unix just proposed the idea of file system, saying that it's an abstraction that we want. And people do buy the idea. So people love file systems and people intensively use file systems. But when people start to adopt that, they figure out, well, there's a performance issue, right? But that's the track of history of all computer science industry. So think about that, right? In the very beginning, we have Facebook. We love Facebook, right? However, at some point, we figure out Facebook is so slow, then people in Facebook start to focus on the performance issue. So in the very beginning, Facebook only had people know how to use PHP and write web programming. That's true. And then later on, and yeah, not kidding you. In 2012, I was attending a programming language conference, and people from Facebook they present how their optimizations on PHP, because they say, well, every program in our company is using PHP, right? But a lot of you who are familiar with PHP, it's not something very efficient. Right? So definitely they change, because when they have the amount of users they've accommodate, right? Now they are talking about faster programming languages or some other things. But the computer science industry is always like this. Let's have the feature roll out first. Once it's popular, we try to improve the performance. So in the very beginning, Facebook is only focusing on getting those features out, and then recently they started to build a whole infrastructure team, trying to optimize for their platform performance. And same thing as Google. So sometimes you guys might say, well, I'm not like people like us, right? We are not on the very front end of each company, but we are actually, when those companies become mature, we are actually pretty desirable ones, because they really want the performance. So again, a little bit off topic. So the thing is that for fast file system, it follows the same track, that they first have the concept of files, and then they love it, but it's slow. So now we have to think about how to make the performance better. And the other thing is that we love it, so we want more out of it. So they want new features. So that's why this paper comes out, right? They want the file system to be even greater. So what are the things they figure out? The old file system is not good enough. First of all, right, when accessing the files, as I said, you have to perform many disk accesses, and even worse than that is that if you think about the layout of the inode, the metadata, the super block, they are in the very beginning. But sometimes, but if you look at the content of the inode, it's actually far away from the beginning, right? So it turns out that it's always the pattern that, okay, I went to the very beginning to find the metadata, and then later on I have to rotate to the data area. But the data area, again, if it's a directory, it gives you the pointer to the metadata of another file, which is again in the beginning of the disk. So you have to rotate again, right? So there are lots of disk 6 because of that. So that's not good. And the other thing is that, right, in our previous example, I just want to get the real content of the file. But it turns out that I have to spend at least 10 accesses, and only one is the one that I need, right? All others are considered as an overhead, right? Because those are metadata, which is not the real data content anymore, right? And limited file size, as a lot of you might be thinking about. And the other thing is that the original design doesn't cover the crash very well, because you only have one copy of the metadata, you only have one copy of the super block data. Once they are broken, everything is gone. And finally, it doesn't accommodate those device characteristics, as I said, because it just gives you a flat label of data disk usage, which is not efficient in many cases. So, wow, this is a list of things that the FFS file system proposed. They proposed a cylinder group, they proposed larger block size, they proposed fragments, and they proposed allocators, and a set of new features. So before we dive into, so we have talked about the why, right? The why of FFS file system is simple. Make it faster, make it better, right? There is no better motivation than that, right? And here are the what's they propose. And remember, right? We said we have this set of problems, right? Lots of things with access single file, the low bandwidth utilization, limited file size, crash recovery, the device of limits, right? So those are these are the whys of the what's proposed here. So now I'm asking you, regarding the mapping between the what and the why, how many of the following statements are correct? All right, let's wrap up in 10 seconds. 5, 4, 3, 2, 1. Time is up. Okay, look at you guys saying. Hello, hello. Oh, what's wrong? Am I having a long graph? Oh, here we go. It's just delay. Okay, so looks like from this graph we need some discussion. So why don't you go ahead and discuss with your friend for another 1 or 2 minutes. And for people online, if you see our TA, don't forget to shout it out. All right, let's wrap up in. Oh, sorry. For some reason, is it working out now? Okay, there we go. All right, 10 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so see what's going on here. Okay, so after discussion, looks like C and D are more popular. So, oh, why do I have a replicated one? Okay, so here's the thing, right? So, okay, I want to hear your voice. So let me see. What do you guys think? How many of the following are correct? 4? 4. Okay. Okay, so which one don't you guys think is the last one? Pre-allocate blocks to improve write performance. So what is cylinder groups? Why they can improve the average access time? You guys are good. Group 1. Group 1. Unlike group 1. So did you guys discuss this time? Mohan, did you guys discuss this time? Hello?
Yeah, there were discussions.
Hello?
Hello,
Did you guys discuss this time?
am I audible?
What?
Am I audible?
What did you say? Okay, so regarding the first statement, what does your group say?
My group said D. I was trying to get the paper, but I'm not able to connect my VPN. So I couldn't verify the facts, but the group was saying the
Okay,
D.
are you guys really? Oh, just
Option D.
repeat what discussion you guys said. That's okay, right?
They were
What, you guys,
saying
what did you hear? Just repeat. You are the repeater. I want to hear it.
1, 3, and 4, as far as I remember it. They were talking
1,
about
3, and 4, as far as you guys are remember. But why 1? When you discuss, not just say, I agree with this, right? But why?
Yeah, I'm trying to get to the paper. I'm not able to reach the
No,
paper.
not about the paper. What they said.
That were the thing. I mean, we were first discussing like what are the points do different people agree on. Those were the points we discussed.
Okay. Okay. So any other group online would like to share? If you don't like to share, I won't send the TA to your group next time. Anyone online? All right. So looks like I have to send a TA to some group next time. I feel like that. I feel sorry about the TA. Okay. So what is cylinder groups? Anyone here would like to share?
So it's the part of this that common files are.
So it's a group of. Is a group of files or say a group of blocks? Right, a group of disk blocks, and we create this group of disk blocks in a certain way. So what is a cylinder group? So the cylinder, right? Remember, right? The name of a cylinder comes from this, right? Is the same track on different disks. So what does that mean? So when I rotate to this place, when my head is positioned on one of the track, then I don't need to move. I can access the next disk, right? Because it's essentially the same position, but just different disk, right? So all I need to do at this time, if the data is right next to each other, if this is, so for example, if I have the data here, if the next block I want is here, all I need to do is not moving. Just use a mouse to select which disk head which disk am I reading from. All set. No move, no sync. So, as you can imagine, what's the benefit? If you can aggregate your group of blocks and allocate data that may be accessed in the nearby future within this group or the same track but maybe next to each other, you can minimize the amount of movements you need to get data. Agree? So you can reduce the sync time in this way, right? So, and sync time is a majority of the overhead for the disk access time. So when you create groups of blocks that belong to the same cylinder, the same track, and if you allocate data that are have spatial locality in terms of accessing pattern, you can potentially minimize the overhead of accessing. So that's the idea of cylinder group. So the cylinder group is that we aggregated these blocks together as a cylinder group, a logically formed group of blocks. And within these blocks, what they have is that I have file system metadata, I have file metadata, I also have the real data. And the file system metadata contains file system information as usual. And the file metadata here only stores the metadata for the files within the same cylinder group. So you can imagine that a cylinder group is like a legal territory, a self-satisfactory legal territory on a disk where you can find everything you need, almost everything you need for accessing the file. And because they are physically next to each other, and you can find everything you need within this group, it minimizes the time of moving the disk head along or moving the disk along. Another thing is that in each of the cylinder group, we have a copy of the super block. So what does that mean? Is that if one of the super block is broken because of a crash or some disaster, there is a high chance that you can still find it somewhere else. And superblock is the most important thing because it's actually about the whole file system. And for file metadata, divisible, sorry, if it's broken, it's just a small set of files broken, right? But for the file system metadata, superblock, if it's broken, then the whole file system would become inoperable. But if I have duplicated copy of the superblock, then even though one of them is gone, I can still have the backup information from other cylinder group, right? So in this way, the design of cylinder group itself is trying to minimize the disk access overhead in terms of latency to avoid multiple sticks every time when I'm allocating data. However, the cylinder group with the idea of replicating superblock also contribute to the feature we want to avoid crash, the disaster when crash occurs, right? So these are the two things that this design can help us, right? So cylinder group is considered, contains the following stuff, redundant copy of the superblock, and it has space for inode. It has bitmaps for free blocks within a cylinder group, summary of block usage, and the data itself. And the most important thing is that it improves the average disk sync time. However, with redundant copy of the superblock, you can also improve the case for crash recovery. So this is cylinder groups, right? So as I said, right, with cylinder groups, you can, because you group this data together, you can actually remove this, reduce the seek time a lot. And if you do it right, it can also help the rotational delay, right? So it's a pretty good design in this one. So now another proposal Unix file system makes is the larger block size, right? So now we want to look at the statement here we mentioned. Larger block size to improve bandwidth, larger block size to support large files. Are those two true? Are those two true? Yes or no? Why yes? How come it will improve bandwidth?
If you're thinking of like streams of data
And
and having a larger block size to increase time.
having a larger block size will what?
Increase the bandwidth of the stream that's being rendered.
Right, so remember what we learned in the last lecture, right? So if every time I put stuff in consecutive sectors, and if that's all what I want, right, then the bandwidth is a lot better, right? So 4 megabyte versus 512 bytes on the same disk, the bandwidth is megabyte versus kilobytes difference, right? So it's 1,000 times faster. Well, not faster, but at least the bandwidth is 1,000 times higher, right? 3,000 times higher in this case, right? So that's why you want larger block size, right? If you have larger block size larger, very likely that you are going to have consecutive accesses over a larger amount of data. So saying that if I set my block size to be 4 megabytes, then every time when I access, because I'm accessing blocks, right? So instead of a sector, right? So I would get 4 megabytes of data each time, which give me better performance in terms of bandwidth, right? So that's actually a pretty good deal, right? And another thing to think about, right? Those inodes, we point to the block addresses. And if you make each block larger, the same address would represent a wider range of bytes available, right? So the total amount of data that you can accommodate within a file still limited, but is at least larger, right? So that's why larger block size would help, right? So larger block sizes actually help on two things. One is the bandwidth. The other is that it helps to make the upper limit, upper bound of a single file become larger. However, as you guys can imagine, right, internal fragments, right? There would be a case that, okay, I allocated a block for a file. However, the file only used a few bytes within a block, but you still have to allocate the whole 4 megabytes. So in Unix system, the fast file system, they actually have the fix to that problem called fragments. So it provides a way that we can further divide the parts within a block into fragments. So you can, if the file content doesn't fill up a block, you can still have the fragments used by other files as well. So that's the idea of fragments. Okay? Now, another thing they propose is the allocator of data. So they have global allocator, which try to find, remember right now we have the cylinder group, we have the concept of cylinder group. So I would say the global allocator is about which cylinder group should I place the file. So in this way, you are selecting a cylinder group that is most appropriate for placing your file. So for example, the cylinder group with the most free space that can accommodate your file. Or try to place your file into as few cylinder groups as possible. So this is the responsibility of the global allocator. And the local allocators are responsible of allocating data blocks within a cylinder group, which try to minimize the amount of the rotational delay of blocks within a cylinder. For example, if my head is right down here, or if the free space of a cylinder group is starting from this place, how can I make sure that the consecutive blocks are placed in a way that it's going to be fit the order of my rotational, the rotational of my disk, right? So in terms of the way how it plays. So you don't want to play stuff that is reverse the direction of this rotation. You want it to be exactly fits the rotation direction of the disk, right? So that's one way that one thing that the local allocators would have to accommodate. So this is the responsibility of allocators. The global allocator is more about which cylinder groups should I place data. And the local allocator is called local because it's responsible for, okay, now you are in my cylinder group, where should I place your data? So those are two levels of allocators that the Unix system, fast file system proposes. So if you look at that, right, how many of the following the fast file system proposes? Cylinder group to improve average access time, yes or no?
Yeah.
Yes. Large block size to improve bandwidth, yes or no? Yes. Improve support large files. Replicated super blocks for data recovery. Last one. No. Why not? Right. So here's the thing, right? This technique was not included because block allocation currently accounts for less than 10% of the time spent in a write system call. And the current throughput rate are already limited by the speed of available processors. So they say, well, write is not a main issue, right? This is what they say. Write is not a main issue, right? And if you were in 203, you learned MDOS law, right? If this is a 10% thing, who cares? Right? So then now, typically, yes.
I have two questions.
Sure.
One of them is regarding the fragments of the blocks. So when we divide it into different fragments, so what happens if we like want a data from a certain fragment and then we figure out that the remaining part of that what we need is in another fragment. So this would make a lot of
so you need, yeah, it will make things more complicated, and you need some kind of bitmap again to indicate, because okay, say although we have fragments, right, but we only partition the fragments into limited amount of partition the block into limited amount of fragments, typically just 8. So you only need one single 8-bit to indicate, okay, where are the bits that we use for storing this. Yeah.
So, but it's still like, since we place it on different places for each fragment, so it would require for us to go from one fragment to another fragment, which would make a little bit overhead of like.
Yeah, you got it. So, in the long run, that will be a problem. In the long run, that will be a problem. So if you're old enough, you might remember there is a program in Windows or Microsoft, those they call defragmentation, because they want to aggregate things together, right? Because if you run this file system for long enough, as you can imagine, there will be a lot of fragments in the system, which is not optimal. Yeah.
And the other question was like regarding like all of this, it's like it requires a lot of work like from the previous.
It's a lot of work from the previous, yes.
So like the system becomes slower.
The system becomes slower. Good question, and it's actually very relevant to the question that I'm asking here. So let me pause the question here and let's look at this question and maybe It will answer your question. Okay, so look at this question. Typically, I don't ask how question, but for this question, I do want to ask how question. All right, let's wrap up in 10 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so let's look at how you guys think about the how question. So, oh no. Okay, so for this, most of you guys think it's C. So why don't you discuss with another friend for another minute, and let's look at what do you guys think after the discussion. Go. All right, let's wrap up in 10 seconds. 5, 4, 3, 2, 1. Time is up. After discussion, what do you guys think? Okay, so a very diverse distribution between CD and E. So definitely we need to hear your voice. And this time I saw the TA was in group 3. All right, so someone in group 3, can you share your thoughts with us? If you saw TA in your group, no matter, don't worry, it's your group. So someone in your group has to speak. What do you guys think? Hello, group 3, group 3, group 3. The TA, did they speak during the talk, during the discussion? Did you hear their voice?
Yes.
Okay. So someone in group 3, can you guys tell us what you guys said? I don't care if you have the paper with you, just repeat what they said. Marcus? Name? Siron? Okay.
So we said that.
Hello, yes, I like to hear you. Okay, what did you hear?
So we said the first one, second one, and third one are correct, and we wasn't sure about the first one, but eventually
So
we
you guys
decided.
think the first and the third are the correct?
Yeah.
So where did you find the evidence?
We actually didn't. We kind of guessed. We were looking for the evidence, so we couldn't.
Wait, but it's actually in the paper, right? Isn't that? Is that in the paper?
Yeah, we couldn't
It's
locate
in
it.
the paper, right? So you have the table, right? So you have this table, right? Okay, but 6 for your insight. Okay. We should really bring people back to the campus. All right, so from this table, what did you learn? So this is the old Unix file system, right? So for the old Unix file system, the bandwidth is at 29 kilobytes per second. The read bandwidth utilization is this low, right? And what did you learn? These are the reads. These are the writes. What did you learn? Is the read performance of the fast Unix file system better than the old? Very good, right? The bandwidth utilization a lot higher, right? How about the CPU utilization? The CPU load? Also higher. Does that answer your question? Right? The CPU load, because as you just mentioned, we have to deal with this, we have to think about this. The CPU load is a lot higher, right? As high as 73%, as you can see, right? Now, looking at the writes, is the bandwidth of the new one better than the write than the old one? Yes, right? Now, compare against each other. Is read faster in the new ones than the old ones? So if you look at the old Unix file system, right, that's pretty interesting. In the old Unix file system, writes are faster than reads. But in the fast file system, reads are way faster than writes. Because of what? Because of the reason they just mentioned. We don't pre-allocate blocks because we don't think write is a big problem. The other thing is that, well, our writes are faster than the old one anyway, so we don't care if we want to make it faster, right? So they do this on purpose. And the CPU load is way higher, but they think it's okay. Because, come on, no pain, no gain, no free lunch, right? You want faster speed. So the CPU load has to be higher, right? And we give you what you want, right? So pay more, that's okay. Right? Does that address your question well? Okay, another question. I love questions. What is that?
So if you're using to that much, then that means that we can't do anything else.
You cannot do anything else, right? But remember the paper that we read. Is it always good to switch to another job? Not always, right? So sometimes, right, it forces us to stay in the same process. And if we can serve this request fast enough, switching to another one, is that really important? Right. So in some cases, maybe not, right? So that's the thing, right? You have trade-off, right? You cannot always say that, well, keep CPU less busy is a good idea, because sometimes, for this case, right, keep CPU busy is probably not a bad idea, unless this won't kill the total system performance, right? Unless this is just a short period of time. All right? Okay, so here, everything here is correct, right? Now, you are structure is about rights, right? Why not? Because it's 10% and rights are a lot faster anyway, right? So, and the other thing which is also interesting is that, remember, right? Remember we said a polling model and the interrupt model. So the rights in fast file system is actually more a polling model than the interrupt model, is that we do synchronous rights. So the write operation doesn't finish until it's a blocking call until the write is finished. And the reason is because they are this way is better for crash recovery. So if the write, if it's a synchronous code, then if it doesn't finish, you know it's not finished. Right? If the write interrupt in the middle, you know it doesn't finish, and then you can deal with that. However, if it's asynchronous, once you issue that, it's out of control. You cannot track the status. So that's why they make the write synchronous in fast file system, because it's also making the crash case more easier. All right. So this is what they propose, and for behind each idea they propose, there is actually a why. So remember, for this class, not only about the what's, you have to figure about the whys, and here are the whys of why they propose this feature. So now we are going to talk about another file system which is more essential, called the design and implementation of the block structured file system. So now, again, I have the question asking you why we have the log structured file system. All right, let's wrap up in 10 seconds. 5, 4, 3, 2, 1. Time is up. Okay, see what you guys think. Aha, some discussion is necessary. So go ahead and discuss with your friend for another minute or two. All right, let's wrap up in 10 seconds. 5, 4, 3, 2, 1. Time is up. So, after discussion, okay, B, C are popular. So, of course, I want to hear your voice. So, what do you guys think about the first statement? It's true. The performance of small random writes. How about the second one? Efficiency of large file accesses? What? True? Second one is true. How about the third one, space overhead of metadata in the file system?
We couldn't find where it's over the space overhead.
Uh-huh.
Just because the metadata is like the same size as the file size.
Uh-huh.
So that's false.
How about reduce the memory space used by the file system? Is increasing. Okay. So let's think, right? So in designing a log structure file system, we decided to focus on the efficiency of small file accesses and limit to so you know what? I think limit to the hardware for large file accesses. So for large file accesses, it's actually not the purpose of the log structure file system because that's where they think will scale with the device. Okay, so but okay, so I think you guys got a point that is worth discussing is that if you think about what the log structure file system does, it's not intentionally doing it, but its side effect actually make the efficiency of accessing large file access larger files become faster. We can discuss about that later, but it's not intentionally on purpose doing this. You didn't mention the overhead of space overhead of meta file, but if you think about to manage the log structure file system, you need more metadata or fewer. Okay, let's put that on shell. And as you guys pointed out, right, it does increase the overhead of memory. And in what way? So look at this, right? So first of all, we are curious about, hey, so in Unix, they say, well, writes is not a big problem, right? But in log structure file system, they say writes are the dominating traffic of disk accesses. We should optimize for writes. Right? The previous paper say writes are not the problem. Here it says writes are the problem. Who is the liar? Who is lying? What? Previous is lying. Second paper is lying. Previous. What's your answer? They are both right. Time is changing. What changes? What changes? Yeah, time changes, right? So here's the thing. UFS is published in 1984. FFS is published in 1984. And this paper is in the 90s. What really changes is that, okay, people typically remember that Moore's law makes a processor faster. But another thing that people typically forget is that Moore's law is actually more about the density of the chip, right? So not only the processor becomes faster, your memory becomes larger as well. So 10 years later, when the time log structure file system was introduced, is actually the time that we have faster processor, we have larger system memory. And with larger system memory, you remember that the Unix, the virtual memory abstraction, they try to cache as much data as possible in the main memory. Reduce the percentage of time you access the disk for reads. And the only thing that you always have to present on disk is actually writes, right? Because whenever you modify something, you want to make sure that your modification it's presented and stored somewhere else persistently. So reads can be safely cached. But for writes, you always have to make sure that periodically my disk has the most up-to-date copy. Otherwise, if crash occurs, nobody can find the updated data. So it turns out that writes are rare. So it turns out that conventional systems, writes are dominating traffic. Conventional systems. When I say conventional system, it's a conventional system for the age of log structure file system. And when you read a paper next week, time changes again. So here, right? So for fast file system, reads are the dominating traffic. For log structure file system, writes are the dominating traffic. So what they do? So first of all, what they propose is this, right? So so first of all, they say that in BSD FFS, when you run it for a long time, this data are still spread out. And the other thing, which is more of a problem, we mentioned that for writes is synchronous, right? And if writes is dominating traffic, whenever you write, the system is holding for the write to be finished. So that's not good enough, right? So what the log structural file system proposed is that, okay, you guys said that it requires more system than memory. How it uses the system memory is that we create a large write buffers and we buffer changes in the main memory system and commit those changes sequentially to disk once a while. That's the idea of log structure file system. So how does that work? It's like this animation. So this is probably the best ever animation I made for explaining log structure file system in this. So I have a write buffer. So see this animation, right? When I gradually, when I'm updating data, the data chunk would gradually be buffered in the system, then memory, and periodically, when I aggregate that to a certain amount, I would present this update to the disk space sequentially as well. And when I finish writing this data chunk, I would attach an inode next to it, right? And why are we doing this? So previously, the Unix fast file system has to do the write synchronously to make sure the data is finishing its update. But for here, right, if your inode is not updated, nobody knows where you place the new data elements. So what does that mean? We made the inode writes as the last step. If we didn't put the new inode, you are still able to use the old inode to access the old version of the data. So if you crashes, at least you have the last version of the data. And the log structure file system is that, right? So keep going, right? If I have another data chunk, right? Again, it will keep aggregating it to a certain degree. And when it reaches that degree, now I hate this animation, right? It will keep appending it sequentially, right? And another inode is attached. So now we set another case. I'm updating data chunk number 1. In the previous design or in the old design, you think we will update the data chunk number 1 here. But that's not what log structure file system will do. What it will do is that we keep appending it. So again, another sequential write. The data chunks are not fragmented, even though it's occupying larger space than the old one. And then you attach the new inode number 1 after you finish the update of the chunk. And instead of doing in-place update, all we need is that we just invalidate the original copy, right? So remember, right? If in this case, something happens when we crash, you can still use the old inode to locate the old version of the data, which is way safer than the previous one, right? And the other thing is that every time you write, it's sequentially written. So in a larger chunk, so the performance is a lot better. So that's the whole idea of a log structure file system, very simple. So if we review this question, the first one is correct. The second one, they say limit to the hardware. But I get your point here is that if you think about every time you write stuff and read stuff And because you write stuff is sequentially in sequential blocks, when you read them, they will also be in sequentially in large blocks. So it naturally makes the performance of reads better, although not intentional. And the space overhead, because you have invalidated version of data, so it's actually larger because you have garbage, you have the bitmap. And it increases the memory usage because you have the right buffers. So that's the basic concept of log structured file system. And sorry for taking 3 or 4 more minutes for the class. And before you leave the classroom, don't forget we have reading quizzes due next Tuesday. We have project due next month in the very beginning. We have office hour for you to address your concern about your project. Other than that, enjoy the rest of your week. I will see you next.